Forget everything you know about travel. Right now, on the ground in China, a machine is shattering the limits of physics. This is the Ultra-High-Speed Maglev, a 1,000 km/h beast that makes a cruising Boeing 747 look like it's stuck in traffic. We aren't just talking about a faster rail line, we're talking about magnetic levitation taken to the extreme. Imagine sitting in total silence while 20 football fields vanish behind you every single second. This is China's $25 billion gamble to kill air resistance by launching this maglev train inside a giant airless vacuum tube. As we hit the critical milestones of 2026, this maglev revolution is no longer a theory. It's a reality that turns a 1,200-kilometer journey into a 90-minute commute. Before we tear open the steel skin of this vacuum-sealed monster to see how the magnets actually work, do subscribe and like the video to join our future tech community. Now, welcome to the age of the 620-mile-per-hour maglev commute. Number 1. The evolution of high-speed rail. China already operates one of the world's largest and most advanced high-speed rail networks, with conventional bullet trains routinely cruising at around 350 kilometers per hour. This established foundation of rail technology, infrastructure, and engineering expertise set the stage for more daring innovation. Unlike traditional steel wheel trains that roll on tracks, magnetic levitation technology uses electromagnets to lift and propel vehicles, eliminating contact friction and enabling smoother travel at far higher speeds. The evolution from conventional high-speed rail to maglev also reflects decades of experimentation in materials, track design, and propulsion systems. Lightweight alloys, precision-engineered guideways, and aerodynamic shaping all contribute to minimizing energy loss at extreme speeds. China's experience with regional high-speed networks, including dense urban corridors, has created both the technical know-how and the regulatory framework necessary to support maglev systems. Beyond technology, operational practices like real-time monitoring, predictive maintenance, and coordinated train schedules have laid the groundwork for managing networks where trains will soon exceed the speed of most commercial jets on short to medium routes. Number 2. Maglev fundamentals: how magnets make flight on rails. Maglev, short for magnetic levitation, works by using magnetic forces to lift, guide, and propel a train without direct contact with the track. Powerful electromagnets on the train and within the guideway create magnetic fields that both float the train above the surface and push it forward. By eliminating wheels and physical friction, maglev systems dramatically reduce energy losses and mechanical wear, enabling extremely smooth and quiet motion. Beyond the basic levitation principle, modern maglev systems rely on precision feedback loops and superconducting magnets in some designs to maintain stability at extreme speeds. These systems continuously measure the train's position relative to the guideway and make micro-adjustments hundreds of times per second to prevent wobbling or drift. Additionally, maglev trains convert electrical energy directly into linear motion without intermediary mechanical components, which improves efficiency and reduces maintenance requirements. Combined with computer-controlled propulsion and braking, this technology allows safe acceleration and deceleration even at speeds approaching 1,000 kilometers per hour, a feat impossible for conventional wheel-on-rail trains. Number 3. The vacuum tube: overcoming air resistance. At extreme ground speeds, air resistance becomes the ultimate enemy. Doubling speed doesn't just double drag, it increases exponentially, creating a barrier conventional trains can't penetrate. China's Ultra-High-Speed Maglev addresses this by traveling inside a partially evacuated tube, a long tunnel where most of the air is removed. This low-pressure environment dramatically reduces aerodynamic drag, similar to how planes fly faster at high altitudes with thinner air. Inside the tube, trains face far less air pushing back against them, allowing speeds approaching 1,000 kilometers per hour without needing excessive energy. Engineers optimize the tube's internal shape to smooth airflow, minimizing turbulence and reducing the risk of sonic booms at ground level. Temperature control is also critical, as heat fluctuations can change air density. The tube acts as a controlled environment, ensuring magnetic levitation and propulsion systems function efficiently while shielding passengers from storms, snow, or strong winds that would otherwise interfere with ultra-high-speed travel. Number 4. Engineering and safety: building the impossible tube. Constructing a low-pressure tube over hundreds of kilometers is one of the most challenging feats in modern engineering. The tube must resist crushing forces from atmospheric pressure, while remaining flexible enough to absorb seismic vibrations and thermal expansion. Precision-engineered seals, joints, and internal supports maintain structural integrity without compromising the vacuum. Thousands of sensors constantly monitor pressure, temperature, tube alignment, and material stress in real time. If irregularities occur, automated systems can isolate segments to restore stability while keeping trains operational elsewhere. Emergency measures include magnetic braking zones, access tunnels for rapid rescue, and redundant power supplies to maintain levitation and propulsion in case of failure. By combining advanced materials, structural engineering, and real-time monitoring, this system ensures that the Ultra-High-Speed Maglev operates safely and efficiently, gliding nearly frictionlessly while withstanding the immense forces of air pressure and extreme speed. Number 5. Control systems. At speeds approaching 1,000 kilometers per hour, covering almost 3 football fields per second, human reaction alone is far too slow to maintain safety. Ultra-high-speed maglev trains rely on sophisticated automated control networks that monitor and adjust every aspect of operation in real time. Computers regulate magnetic levitation and propulsion fields hundreds of times per second, keeping the train perfectly centered, stable, and ready to accelerate or brake instantly. A dense network of sensors along the tube continuously collects data on train position, speed, tube pressure, temperature fluctuations, structural vibrations, and even electromagnetic field strength. If any deviation is detected, automated systems can seal off sections of the tube, adjust air pressure, or gradually slow the train to prevent accidents. Advanced predictive algorithms also anticipate potential obstacles or tube anomalies before they affect performance, while redundancy systems ensure backup control if a primary system fails. This level of automation makes ultra-high-speed maglev operation not only feasible but safer than traditional high-speed rail, transforming human oversight from direct operation to strategic monitoring. Number 6. Testing progress. China's ultra-high-speed maglev program isn't theoretical, it is built on progressive, real-world testing. In 2024, engineers successfully demonstrated a full-scale maglev vehicle running inside a short, low-vacuum tube, proving stable levitation, smooth propulsion, and effective braking under low-pressure conditions. This initial test validated critical systems including magnet calibration, tube pressure control, and emergency response protocols. By late 2025, prototypes achieved speeds near 700 km per hour on open test tracks, setting new records for ground transportation. These vehicles incorporated lightweight carbon fiber bodies, aerodynamic nose designs, and optimized magnetic coil arrangements to minimize drag and energy consumption. Each test also refined control algorithms, tube air management, and emergency braking sequences, moving closer to the 1,000 km per hour target. Planned demonstrations in longer, low-pressure tubes around 2026 aim to simulate full operational distances, demonstrating the practical feasibility, safety, and repeatability of sustained ultra-high-speed travel. This rigorous approach ensures that when the system is ready for public or commercial use, it will operate efficiently, safely, and reliably, setting the stage for a new era in rail transport. Number 7. Infrastructure challenges and global implications. Building a nationwide or even regional network of low-pressure maglev tubes is a massive engineering and logistical undertaking. Unlike traditional rail, these systems must maintain a stable, low-pressure environment over hundreds of kilometers, which demands airtight tube construction, robust materials to resist deformation, and continuous monitoring of structural integrity. Construction must account for seismic activity, soil shifts, extreme weather, and thermal expansion, making civil engineering far more complex than conventional projects. Integration with existing transportation networks is also critical. Stations, transfer hubs, and cargo terminals must be redesigned to accommodate trains that move at almost 1,000 kilometers per hour. The global implications of such a network are equally monumental. Travel times between cities shrink dramatically, potentially surpassing short-haul flights for convenience and speed. Entire regions could merge into mega-regions, where economic activity, labor mobility, and cultural exchange occur at unprecedented rates. Supply chains would become ultra-responsive, with essential goods, medical supplies, and industrial components transported almost instantly. The success of China's system has caught the attention of countries like Japan, South Korea, Germany, and others exploring similar ultra-high-speed rail possibilities. If scalable, this technology could redefine urban planning, international logistics, and regional economic strategy, sparking a new era in global connectivity that merges cities, industries, and people at speeds previously thought impossible. Number 8. Life in the ultra-high-speed era. A fully operational 1,000 km per hour maglev network would transform daily life and societal structures. Trips that once required flights, overnight trains, or multi-day travel could now be completed in less than 2 hours, fundamentally reshaping how people live, work, and study. Students could attend universities hundreds of kilometers away while still returning home on weekends. And professionals could reside far from their workplaces without sacrificing family time or lifestyle. Families separated by geography could maintain regular contact, while businesses could operate across previously impractical distances. Cargo and logistics would experience a parallel revolution. Critical medical supplies, emergency response units, and time-sensitive goods could be deployed almost instantaneously, saving lives and boosting economic efficiency. Urban and regional planning would evolve as city clusters merge into interconnected mega-regions, blurring the boundaries of traditional metropolitan areas. Beyond convenience, this technology reshapes society. Commuting norms, regional economies, and even social interactions would adapt to ultra-high-speed mobility, similar to the societal shift caused by the invention of high-speed rail a century ago. The maglev era promises not just faster travel, but a complete reimagining of space, time, and human connection. Ultimately, we are standing at the absolute threshold of a new era in human mobility. China's ultra-high-speed maglev is more than just a faster way to travel. It is a final declaration that the physical boundaries of our world are officially shrinking. By successfully merging magnetic levitation with the silence of a vacuum, engineers have effectively conquered the two greatest enemies of speed: friction and air resistance. We have witnessed the evolution from traditional rails to a $25 billion flying train that bridges the gap between ground travel and aerospace technology. As the milestones of 2026 turn these low-pressure tubes into a reality, the death of distance is no longer a theory, but a 620-mile-per-hour heartbeat that connects mega-cities in the time it takes to finish a meal. From the record-breaking tests in Shanxi to the futuristic flying saucer hubs, every innovation we've discussed proves that humanity is no longer bound by the limits of the atmosphere. On the tracks of tomorrow, space and time have finally met their match, so the future of travel is no longer a destination we are moving toward. It is a reality that has already arrived.